Well, good afternoon, everyone, and welcome to a joint EOL-RAL seminar. I'd like to welcome Dr. John Hubbert, who has been leading a successful and productive career as a project scientist with RSF, the remote sensing facility here at EOL. Scholastically, John did his graduate work at Colorado State University with a master's and PhD in electrical engineering. He is currently the PI for NCAR's NextRad data quality program funded by the National Weather Service. NextRad stands for Next Generation Weather Radar System, which is a network of S-band Doppler radars that detect precipitation and wind. John holds several patents in radar filtering methods and has numerous publications. I've counted about 90 of them in the realm of radar polarimetry. I always have problems with that word. His expertise and research interests include radar signal processing, microwave remote sensing, antennas, and propagation. All of this knowledge lends to his seminar today, in which he will delve into global regression filtering. For those of you watching online, please type your questions into the Slido window, which is located past the bottom of the presentation screen. We're going to save and read those questions out at the end of this talk. So Dr. John Hubbert, the stage is yours.
Again, thank you for attending and people that tuned in over the internet. And again, I'll be talking about global regression filtering. This research is a product of this NextRad data quality project that I have been involved with since I've been here at NCAR. And I'd like to give thanks to Greg Mamaris, Ulrike Romashke, Mike Dixon, and Scott Ellis, who have been involved in this project. So let's get into it. I guess I have to down there. There we go. So typical regression analysis. So when you look at regression analysis, you might typically come to mind with these graphs I show here on the bottom, where you have some kind of a scatter plot and you're doing some kind of a curve fit to it. And so regression analysis is a set of statistical methods used for the estimation of relationships between a dependent variable and one or more independent variables. Very broad definition. And it's used to basically quantify the relationship between the variables. And so, but as you'll see, that's not what I'm talking about. And so let's move on to what I'm really talking about, and that is really polynomial fits or regression fits using polynomials to time series data. And they're not scatter plots, and two time series are shown here now with the black curves, and then the red curves are regression fits that predict the trend, you might think, of these two particular time series that I'm showing you here. And so I'm going to examine this operation in terms of filtering and frequency responses, much as you would if you were looking at FIR-IR filters. And why do we want to do that? Well, over the past 5 years and even more, we have been rethinking ground clutter filtering. And there is a ground clutter signal, that's the lower center of the screen, and you can see it's a very smooth varying function. And so we want to be able to, identify that and to, predict that and to get rid of that clutter filter. And the question is, well, could regression filtering, work in this case? And before I really jump into the more meat of the presentation, I think it's it's beneficial to take a look at the brief history of radar clutter filtering and why we are where we are today. Well, we've got to go back to the beginning, and in the beginning there were a few choices really for clutter filtering back in the 1960s. You could do clutter identification by hand, maybe. You use line printers to get graphics, or maybe an A-scope. You could take a look at the data, and what's a filter? I mean, there was no filtering going on back then. So this was the very, very beginning. radar, weather radar data. Then came the dawning of computer technology in the 1970s. Man began to realize the potential of computers. Could this technology make possible the recognition of clutter? Clutter recognition and filtering back then primarily focused on the pulse-to-pulse power difference of our return signals, and that's because weather signals typically vary pretty rapidly, but ground clutter filters are very slow moving, and based upon that difference, you see that pulse-to-pulse difference could be able to identify and perhaps filter clutter data. Then came the dawning of the age of Aquarius. I guess you guys know who the fifth dimension is. In the next decade, ideas of fuzzy logic and neural nets evolved. Could these ideas identify clutter contamination, and could it be filtered? People started investigating IR filters, infinite impulse response filters, but technology to implement this in real time really lagged behind. So people started thinking about it, but it was kind of difficult to do. And as soon as you get computers involved, man had a love-hate relationship with computing, because it never works out, does it? So moving on, technology improved and IR filtering became possible in the 1990s, but man was not satisfied. What do I do with an IR filter? Filter everywhere or not at all? See, IR filters, they work nice with a continuous stream of data. And for radar clutter filtering, we like to look at individual gates to clutter filter. So you're kind of stuck with, am I going to clutter filter this or not? And then if you did clutter filter it, you had to have a beam width. You want to use a 3-pole, 4-pole, or a 5-pole filter. And so you could see things weren't very good yet. It was not very ideal whatsoever, and we needed more power. We need more speed. And so we were launched into the modern era around 2000. We had fast processors, do real-time processing, digitization, archival, time series recording, and most importantly for this talk is that we had adaptive, real-time spectral processing. We could calculate the spectra of these signals and take a look at them and manipulate them in real time. So, and the ability to adjust the filter bandwidth on a gate-by-gate basis, very important. And then also there was an ability to do interpolation across that zero velocity gap. And so the filter that the National Weather Service used is called GMAP. And in fact, there is a paper from ERAD, the European Radar Meteorology Conference from 2002, that describes GMAP and is much referenced, and the authors are Fritz O'Hara and Richard Passarelli, who manufactured and sold the SIGMET signal processor to the Weather Service. And so life was good. Hey, we could do all this spectral processing in real time, and we had adjustable bandwidth. We could reduce the biases of the weather signal, and so pretty much people were happy. But man still was not satisfied. Spectral clutter filtering requires window functions. And there is the window function monster, and he's saying, I want your independent samples, because that's what he does. He eats up your independent samples. And in fact, using a Blackman window, you lose 5.3 dB of your signal by putting a Blackman window, which is required on clutter filtering. And that's a lot of signal to use. What would you do to get 5.3 dB more in any of your instruments that you work with? That would tremendously improve your data quality. So not a pretty sight. And so we need to come up with a better solution here. So next generation clutter filter, says me, is regression filtering. And I really think this is a paradigm shift that we need to go through for clutter filtering. So what is regression clutter filtering? Well, I've alluded to it, and you might be able to figure that out. So I'll give you an example. So here is a clutter and a weather signal. The weather signal varies rapidly. You can see the oscillations. And there is the clutter signal it's riding on top of, and it's just smoothly varying in there. So what do? You've got to go ahead and pick a polynomial order of the appropriate order, a polynomial fit for it with an appropriate order, and you do the fit, and so there you see the red curve, that's the clutter signal. Riding on top of it is the weather signal, and you simply subtract it. And voila, there it is, there's the weather signal. And that's exactly what weather signals look like. So that's all there is to it. It's really almost stupidly simple, and I'm really surprised that people haven't gone toward that sooner, but I know why, and I'll get into that in the rest of the talk now. So we need to take a look under the hood. Let's see what's going on with this, with these clutter filtering techniques. So the fundamental issue is how to represent the clutter signal. That's what it all really revolves around, i.e., what are your basis functions? What basis functions are you going to use to try to represent the clutter filter? So then you can take and eliminate those basis functions, right, that contain all the clutter. And so here are the two methods right here. Representing clutter with orthogonal, because you always want to use orthogonal basis functions. On the left are the functions we use, or I use, or our group uses for regression filtering. They're orthonormal polynomial basis functions, and they are the Forsyth polynomials, which have only been around since 1957 is the paper on this. So it's not like this is real sparkling new technology. And so I'm just showing the first seven basis functions, and we are going to represent the clutter using those basis functions, okay? And so you can see that clutter is a slow varying signal, right? So you have one of the basis function is a constant, then there is a straight line or a linear line. You can see that's the curve labeled B. I probably can try to point to them here a little bit. And then here is the quadratic, like a parabola here, and then the green one I think is the next one. And so you see you have a lot of basis functions that vary not very little, or they're very slow varying over this interval, and these basis functions are restricted to that interval. So they make kind of a good way to represent slow moving clutter signals. In contrast, as used by GMAP with the spectral method, you use the Fourier transform. Very, very typical analytical tool. And I'm just showing you a few of the sinusoids that are going to be used as part of the Fourier representation of the signal. So down here is the Fourier transform pair. And so you use the DFT, it's called discrete Fourier transform, or the FAST technique, the fast Fourier transform. And so you can take and represent your time signal as a sum of these sinusoids. Okay, and so that's the difference between the two techniques. But you have to use a Fourier transform. And so what does that mean when you have to use a Fourier transform? What does this do to our signal? Well, here in the green box is a clutter signal from S-pole. And so if you go ahead and you take a DFT or an FFT for the algorithm, you actually turn it into a periodic signal because it's a sum of sinusoids, and the sinusoids are continuous and periodic. You've just created a periodic signal. Now look at this periodic signal. Between each period, you have these big jumps. And if you're going to represent those jumps with a sum of sinusoids, well, guess what? You have to use a lot of high frequency signals to represent that. Even though the clutter signal itself is very, very low frequency, you take the FFT of that signal, you're going to end up with a lot of high frequency content. And so that's just what I said there in the term. And so this, if you would take and do a Fourier transform of that raw time series signal, that's what the spectrum would look like. And many, many of our clutter signals, that's what they look like. They have this weird tent type of structure to them. And so that's what I'm speaking about again. And what causes this tent is, or this tent thing, we term that clutter leakage. Instead of the clutter signal being around zero velocity where it should be, or where we know it is, it gets spread across the spectrum because of the discrete Fourier transform. So what's the solution to that? It's very well known, nothing new here whatsoever. You take and you put a Hanning window on the time series. And so the bottom periodic signal is the same signal as up above, except it's had that Hanning window applied to the real and imaginary parts. So now you see you've gotten rid of that step discontinuity. And so you get rid of the clutter, the clutter leakage. I'll have some examples of that. In fact, here's an example here. We have the raw spectrum on the left-hand side, that weird tent formation, and there is the real part and the imaginary part of that sequence, okay? And that is slow moving, so that looks pretty much like clutter. And then, however, writing on top of that, there is a weather signal down in there. And so we'd like to get at that weather signal. So let's go ahead and compare the two techniques. First, we'll take a look at the At the regression model, we're going to do an 8th order fit to it, both the real and imaginary parts. There's the red line, there's the fit, you subtract them, and once you do that, there are the residuals. So you can see this oscillatory behavior of the signal. That's the small weather signal that's riding underneath there that we'd like to make an estimate of. And so the regression here is the regression filtered signal, and there was the raw spectra. So the regression filter works pretty nice. It actually brings out this signal that you would not see from the raw spectrum. So that's the action of the regression filter. Let's take a look at the same thing now. We take those same time series. You're going to use a Blackman window on it now. And when you put a Blackman window on it and you take an FFT of it, that's what it now looks like. Doesn't look like a tent anymore. You can see the main clutter signal. You can see the little weather signal sticking up there. And notice that the noise floor is way down. And that's because all that noise that was out along the skirts, because of the Blackman window function, has pushed that back in around 0 velocity. And so then it's easy to filter, right? And this was the attraction of this method back in 2000. You just could go in there and it's easy to see. You go ahead and you just notch it out. And once you notch it out, then you're left with your weather signal and the clutter is gone and you can go ahead and do the estimates. And so here's a comparison. On the left, that signal when we did regression processing on it. On the right, when we did the window and notch or the GMAP type processing on it. And they do look pretty similar. They both end up with that same, same weather signal. But why regression? We go back to our Blackman window monster that was eating all of our independent samples. And what does that mean? Well, you put a Blackman window on that thing, you end up with 5.23 dB of attenuation, and you have about a 50% increase in variance of your estimates. That's a lot, 50%. If you use a Hanning window, not quite as aggressive as Blackman window, you end up just 4.9 dB, which is still a hell of a lot, right? And you only get 35% increase in variance. Still a lot of increased. Well, so that's why we are so interested in regression filtering. It's been looked at before. Regression filtering has been applied to blood flow detection in the biomedical field, and I just wanted, not like we came up with this at all. This was back in the literature. Here's some dates going from 1991 to 2002, and in case you're interested, you can look up these articles, and they'll talk about regression filtering, and then they'll compare them to FIR and IIR filters. So it's been done before. Interestingly, though, it's also been done in weather radar. It's done by this fellow named Sebastian Torres, whom we know very well, and Dusan Zernick. He's a giant in the field of weather radar meteorology. And in their 1999 paper, they addressed ground clutter cancellation with a regression filter. But this was back in 1999, and remember, that's when GMAP came on board. And GMAP not only did the clutter filtering, but then it had the adaptive bandwidth, and it also had the interpolation, and it was all inside a package sold to the Weather Service with that Sigmet RVP8 processor. And so they just took the whole package, and that's why we're using it still today, because the National Weather Service adopted that. And there's nothing wrong with it. It works very, very well. It's been an excellent clutter filter, except it does take away 5.3 dB of your signal. Okay, let's take a look at some theoretical aspects here of regression filtering. So it's very different, regression filtering. You do curve fitting to endpoints. It's very different than an FIR, IIR, or a spectral window and notch filtering. FIRs and IIRs can be characterized by a convolution product for you people that are a little more familiar with filtering series. So in other words, you can take a convolution product of the filter coefficients and with the input signal. And for example, convolution in the time domain is multiplication in the frequency domain. Anybody that's tread around in electrical engineering, this is real fundamental stuff. And we like it. As electrical engineers, we like this. This is good. Convolution in one domain, a multiplication in the other domain. We really understand this stuff. And so we like it. So we like to stick to it. A regression fit to the endpoints cannot be represented as a convolution product. I've looked all over everywhere. I don't know of anybody that can represent a global fit and a regression fit to some data with polynomial and represent it as a convolution product. And you see the engineers said, well, it's kind of nice, but with no convolution, we don't like. And so, however, we'll go on here and say that the regression filter is linear. And linear, here's the definition, that if RF here is regression filter, your regression filter A, you get an output capital A. So therefore, if your regression filter an A signal plus a B signal, you just get the individual output summed together. Or if you take and you multiply a constant time the signal and regression filter, you'll just get that constant times the output A. That makes it linear. And I will argue or state that if our RF is time invariant, because linear time invariant filters are what we really like, and I will say that the regression filter is time invariant in the sense that the time location of the same endpoints that you filter will give you the same output, whether you filter them during this time or you get those points during this time or later. And so in that sense, it is time invariant. Okay, well, if it's a linear filter, you should be able to get a frequency response out of them. And so let's talk about the frequency response. And I don't want to delve down into the mathematics here too much, but here's a representation in the time domain of that filter, B sub t. B, these are the polynomial basis functions, and you can take a Fourier transform of that. And here is the representation of the frequency response of a regression filter that I've been talking about. And this is found in a couple of papers here. This Torp guy from the biomedical division and Torres and Zernick also cover it in their 1999 paper. So this is the formulation. If you want to calculate the Fourier transform, it gets you into the frequency domain. It shows you the frequency response of the filter itself. Another way to do it, and this is something that we did on our paper, which is listed down here. It's a recent publication, 2021, has all the details. But fundamentally, let me skip all what's written there, but you simply have a plant, and then you take noise, and you pass it into your plant, your filter, and then you get an output. Well, what your filter does to that signal will be seen in the output, and you simply pass multiple pure white noise signals through that filter, and you build up maybe 1,000 or 5,000 outputs, and you average all those spectra, you'll end up getting the frequency response that way. And I particularly like this technique. I don't really have time to go into it, but there's a couple of ways to get the frequency response, and the frequency responses are nice because it gives us a tool, it gives us a handle to understand what our filter is doing to the signal. And so here is the frequency response for 64 points, minus pi to plus pi radians, across plus minus the Nyquist interval, versus the attenuation as a function of the polynomial orders, odd numbers, 3 through 19. And as you see, as the low orders are blue, and as you increase, you go out to red. So as you increase your order, you get nice little increments in its ability to filter out the signal. So this is the way you control the bandwidth of your signal. On the right-hand side is simply an exploded view of the curve on the left-hand side. And to get those continuous looking curves, we use zero padding, not important, but marked in those little dots are where the actual discrete 64 points are located. So this is for 64 points. You can do the same thing for 32 points. Notice that for the same regression orders, you get actually wider bandwidths. That's how regression filtering works, how polynomial regression filter works. You take it down to 16. We only go out to order 9, and you can see how wide those are. Those bandwidths are getting, and so. But the important thing here is that the frequency response gives you a way to characterize what your filter does to the signal, and it gives you a way to decide what order filter do I really need to filter this signal to get the desired results that I want to get to. So I mentioned this is all global regression filtering I've been talking about. So what the heck is local regression filtering? Well, local regression filtering, you'll actually find this is covered all over in the literature, and there's not much will ever be seen about global regression filtering. So a search on regression filtering and analysis for frequency analysis or with convolution invariably will lead you to local polynomial regression. That's what people talk about. And the one that's the most familiar, people, if you've ever done this type of signal processing, is this filter called the Savitsky-Golay filter. And local, what do they mean by local? Well, you have a signal that's, let's say, is this long. So that's the length of my signal. That could be 100 points. And what we're going to do is going to take a window of maybe only, let's say, I don't know, 10 or 15 of those points. And then we're going to take and do a polynomial fit to those, let's just say 10 points. And then that middle point becomes the filtered point. Take that window, advance it one, do a polynomial fit again, take the center point, that's the next filtered point. And so you just march through the whole data like this with your window function doing these little polynomial fits. And the most well-known one is Savitsky-Golay. And why do this technique? Well, Savitsky-Golay is maximally flat at 0 frequency. It does a really good job of smoothing a time series while preserving the high frequency components for some applications. And it can be formulated as a convolution. In other words, like an FIR filter. So actually, Savitsky-Golay is nothing more than an FIR filter. And in fact, you can those kernels, you know, those little windows I'm talking about, you can go ahead and calculate those coefficients, and then you just apply it like it's an FIR filter. So why do people like local regression filtering? Well, you can represent it as a convolution, and it fits back into that linear time invariant filtering theory, and that's what us electrical engineers really like. And this is a reason why global regression filtering has been kind of bypassed, because it doesn't fit into that little notch of linear time invariant filters. If you want a little more insight on this, there's a reference down there at the bottom by Schaefer, R.W. Schaefer, Oppenheim and Schaefer. Some of the old-time signal processors here may recognize that. That's one of those, I had that as a textbook way back when I was in graduate school. Okay, so why have global regression filters? Why have I pretty much have told the story already, it turns out. So why have global regression filters been overlooked? They do not fit the traditional form of FIR or IR filtering. Consequently, literature on regression filtering go directly to local regression filtering, where convolution and impulse response and all these ideas can be applied. So just to pound this concept farther home here, global regression filter, you fit the polynomial to the entire length of the time series. Local regression filter, you filter a subset length of the time series, and you use a sliding window approach going across your signal. But don't do that. That's not you won't get very good results when you clutter filter using a Savitsky-Golay type filter. It will not give you the good frequency response that I showed you before. Okay, regression implementation issues. Well, you remember back why GMAP was so popular. Well, you could go ahead and you had an automated bandwidth selection by going into the FFT. Do I notch here? Do I notch here? Maybe a notch here this time. And so you could switch your notch around to fit whatever clutter signal you had at your particular radar resolution volume. And so we need to do the same thing with a regression filter, and I think you can see how we're going to do that from my frequency responses. And then design an interpolation scheme to go across the zero velocity gap. There was a real specialized interpolation scheme embedded into that GMAP filter that the Weather Service still uses today. Okay, we've done those two things, and we've moved on. But let me talk about the regression order selection. The regression order selection depends upon the length of the time series. It depends upon the amount of clutter power you have in the signal. It depends upon the clutter spectrum width, or the clutter spectrum width divided by the Nyquist velocity or the folding velocity. And that clutter width is a function of the scan rate. Well, as it turns out, we know all that stuff, before we start our scan or as we start our scan, and for each individual volume, resolution volume, you can go in and take a look at the signal that's around zero velocity and a couple different techniques, and you can determine how much clutter is in each spectrum. So this some nice work done by Greg Mamaris, and this is how we select our polynomial orders for each resolution volume. And so what he's done here is a number of simulations over that parameter space that I showed you, the number of samples, the spectrum width, the clutter to noise ratio, the Nyquist velocity, and made a plot of the normalized spectrum width clutter there in the bottom axis, and then on the vertical axis is actually the order normalized by clutter to noise ratio raised to the 0.67 power. We don't know quite why 0.67 works so well, but it makes all these curves lay on top of each other, and each one of the colors is for a different clutter to noise ratio. But because of this, we can know these parameters. We can go ahead and then select the regression order we need to use for filtering. The Gaussian interpolation, this is very straightforward. You have a notch. This is my notch now where I filtered it out. We use information left over in the spectrum to predict a Gaussian fit. And so this is quite simple to do, and we've done that already also. So let's hit on this polynomial fitting here. Again, you need to use a set of discrete orthogonal polynomials. Not all orthogonal polynomials are discrete. Legendre polynomials are not discrete. If you go ahead and you discretize those, you have to do some special techniques to make sure that where you discretize those basis functions, that they're actually going to be orthogonal to each other. The best thing to do, in my opinion, is you go ahead and you grab some polynomials that were defined in a discrete domain, like my favorite Forsyth polynomials, and go ahead and use those. If you're interested in trying out this technique, or you want to get a hold of this algorithm, you can go to this gentleman's. He's an old-time engineer fellow out of France, and he has this web page, and we'll talk about his Forsyth polynomial and all sorts of other numerical techniques. It's kind of a fun page to have. And more importantly, though, he has the code there. And really, really more importantly for me, he has the code in Fortran. So it's hard to find good code in Fortran, but this is a remarkable program, how well it works. So don't be afraid of higher order fits. For 64-point sequences, there's kind of a bit of a myth out there. You can't, high order fit, it's going to become unstable. We better not do that. It's really a myth. You don't have to worry about that. A little bit when you get really tall, really high order sequences or high order polynomial fits. I'll talk to that in a minute. But for 64-point sequences, I typically use the 37th, 47th order. Last week, for the fun of it, I just tried a 63rd order fit to 64 data points. No problem. Matched them up. Not an issue, because the algorithm, so I can go just briefly into that. Typically, if you're going to do a polynomial fit, you have a matrix in there that relates the input to the output. And so you have to take this matrix, and then you have to calculate the determinant, and then you invert it and all this stuff. Well, if the polynomials are in fact orthogonal, that takes that matrix and it makes it diagonal. And so then it's just simply a multiplication algorithm. You get rid of that inversion process and a lot of arithmetic, and it's all those arithmetic operations that have uncertainty to them that drive up the error on it. So again, discrete orthogonal polynomials is where you want to go there. So let's look at something here. Maybe some people are falling asleep, and I better show some data now. So here's a comparison of the regression and the GMAP-like filtered data. Let's use our favorite instrument, SPOL, right? Everybody loves SPOL. So here it is, SPOL from March 13th, 2019. This was the famous bomb cyclone that came through back then. I don't know if you remember that or not, but that's reflectivity. I think that should be the 0.5 degree elevation angle. There are the Rocky Mountains on the left-hand side, big heavy-duty clutter, all that yellowish brownish stuff there, more yellowish, I guess, a little red tinge on it. All that is clutter, and you can see the clutter is embedded into this large spread precipitation system that's moving into the area. So let's go ahead and we're going to clutter filter that now. So first of all, we just don't clutter filter everywhere because that you do destroy your zero velocity isodop, right? Throw away weather. And so we have an algorithm called CMD that we developed in our group that's currently running on the NextRad radars. And all of these red areas are where we're going to apply the clutter filter. And so I'm going to pick out 2 areas for you marked with these ovals where we can compare the regression filter data to the GMAP, the spectral and notch filter data. So let's take a look at those now. First, I'll give you a quick look here at the automated order selection. Here are the orders, the red ones up around here, 10 to 12. The green ones are around 6 or 5. And so depending upon how heavy the clutter is, we'll use a higher order. And if it's light clutter, we know smaller power coming from the clutter, we'll use a lower order filter. So that's nice to be able to do that. So on the left-hand side is the GMAP, like our own version of GMAP we use here on SPOL. That's filtered. And on the right-hand side is the new regression filter data. And so take a look and compare with your eyes. Then I'm going to go back and forth between the 2 white ovals and the 2 black ovals. Which data set looks better? Regression. Yes, I knew it. And so you can see it's really easy, right? You can just see that it's a superior filter. Look how much smoother the data in there. Now, to be fair, I don't want to fool you, is that this hand window has been applied everywhere on the left-hand side to show you, even where there's no clutter filter being applied, you can take a look and see what just that hand window does to the data quality. It reduces the number of independent samples. And so if you take a look around in like these areas over here, I think I lost my pointer. Can you see it? I guess it's all right. When you compare it to over here, you can see that the regression filtered, it's not even filtered, it's just, the difference between calculating the moments directly from the data as compared to calculating moments from data that has had a hand window applied to it. So it just shows you the detrimental effect that these window function has on the data. So I'll go through the rest of the variables here, but it's all showing the same thing. Compare the 2 ovals. Rho HV is very sensitive to noise, and you can see the tremendous difference in this field between the 2 ovals. Here is ZDR, pretty much the same. You can see the regression filter data is smoother. And then take a look at FDP, our beloved differential phase. Again, really quite a striking difference here. And then velocity. And it's the same, so it's very, very easy to see which data has superior data quality. And so that's the story for clutter filtering. But we still have time, and so I'm going to try to take this now to some other applications for a regression filter. And this is one that I'm particularly fond of here. What about band pass and band stop filtering? Typically band pass, band stop, here you have your spectra, and what we were looking at in zero velocities here, we were looking at, chopping out signal that are right here at zero velocity. Well, what happens if you have a signal that's out on the left wing or out on the right wing? You want to filter that. Well, that would be more of a band stop, band pass filtering, and for an arbitrary frequencies. And this is where FIRs and IR filtering typically are used. Or you could use an FFT and you could go notch those out. And so regression is not applicable to band pass or band stop filtering. Oh, here comes back our friend Yoda, and he's thinking, he says, oh, maybe not. Maybe it could be. Maybe it could be applied. So let's see how we can do that. So regression, consider a time series with 2 distinct frequency components. So once again, I'm showing you a spectra. And you have a component here around zero velocity. You have another bigger component out here, out toward the Nyquist interval, or Nyquist rate, I should say. And so can we use a regression filter to get rid of that component? And so what I'm proposing here is that you take that input signal, and I'm going to take and do a frequency shift, one of those Fourier transform pairs that we all know, and modulate that frequency that we want to filter to 0 velocity. And that's over here. Then you can apply the regular regression filter to it. And then after you're done filtering, you just demodulate the signal, multiply by e to the minus j omega t, and then you get your output signal. Sounds simple, right? Well, it actually is. So first, let's go ahead now and actually do it to that signal. So here is that original spectrum here over on the left-hand side. And here is a signal that we want to get rid of. So its central frequency here is omega naught, I'm calling that. And so let's multiply that signal by e to the j omega naught, or maybe it's minus j omega naught. I forget where the sign is needed. And there it is. Now we're at 0 velocity with that signal by simply multiplying by e to the j omega naught. Nice. And so now here we go ahead and we applied a regression filter to it, and then we filtered it out because it's at 0 velocity. It's very easy. You apply a regression filter of the right order. So you get rid of that signal, and then you go ahead and you multiply by the opposite sign, e to the minus j omega naught, and it's shifted that one that was at 0 velocity back down there, and there is our notch out there in the wings. So here's a really pretty interesting way to do bandpass filtering with a regression filter, and you don't have the problems of a window function with a window and notch technique. FIR and IR filters, have these problems at the beginning and the end of the sequence because you have filter taps that are not completely filled with signal, so you end up with problems there. But with regression, you're just using the data set that's given to you, and it doesn't matter where it stops or begins. So that's pretty nice. And so there's before and there's after. So indeed, Yoda was right. You can use regression filtering to eliminate anything. So you can actually, there is an application to that, and there is a technique that is used on our national network of radar. It's called SZ864 phase coding. And what phase coding does is you put a phase onto a transmit pulse, the right phase in the right order. And what happens is that, as you know, as a signal goes out and comes back, you receive the signal, but that pulse that you transmitted continues on out into space, and you can get multiple trip echoes coming back at you. So you get these overlaid echoes. And so SC phase coding is a technique where you can separate those echoes from first, second, third trips, et cetera. And it's a good technique, and they use it on all the next rads. In fact, our group helped develop that back 15, 18 years ago. So depending upon the pulse repetition time, weather radars are prone to multiple trip echoes. And so how this algorithm works, you don't have to really completely understand this, but you have these overlaid echoes, and we suppose that you know which one the strong trip is in, and you've cohered to that strong trip. So you identify the strong trip echo, and then you modulate that echo to 0 velocity because you want to get rid of that strong trip echo. Then you use a regression filter to eliminate the strong trip echo. Then you take, and after you've eliminated the strong trip echo, you can go ahead and then undo that modulation that you just did, and then you go ahead and you cohere to the weak trip, which has a different phase code on it because it was in another trip, and then you can go ahead and estimate the weak trip velocity on it. So we can do that. I won't go into a lot of the details, but I just wanted to show you that we have applied it, and indeed, this bandpass idea indeed works. Here are the filtering parameters that we use, but let's just go here and take a look at some results. This SC phase coding actually stands for Sachidananda and Zernick, who developed it back in 1999, I think. And this is here's a simulation now. This is all simulated data. The bottom of it is the width of W1 means a strong trip. So as a function of the spectrum width of the strong trip echo versus the ratio of the strong trip power to the weak trip power, you see all these colors, and all these colors stand for a standard deviation of the estimate, okay? And so as for those set of parameters that I showed before. And so these are coming in here, I forget what, a little under 2 meters per second. But if you go ahead and you do this, and this uses a window and notch technique to get rid of them. The important thing is that they go ahead and they use a handing window on the data, and they throw away 4.9 dB of the signal. So if you use a regression filter, you can avoid that. And this is for an order 37 a filter to take and eliminate that strong trip echo. And you can see that this is much darker colors, much lower standard deviations, and the standard deviations here are about 55% higher than what we see with our regression order. You do, however, see there's a little less recovery area, even though the statistics are much higher in this area. But you can use a higher order regression. You lose some of the advantage in standard deviation, but you do expand it. And so what we're suggesting is that if you can take an estimate, and if your signal is down, in this area here, you would use maybe an order 37. And then if your signal was out here, it had a particular large width, or you had a very high power ratio, you could go ahead and use order 47. So it's pretty remarkable, how well this thing works. So not only does it look like it works in just that initial theory, but it also works on these types of SC phase coding. So we're actually currently taking and using that data, or using this technique to process some NextRad data and try to make some good comparisons there, and we're not ready to show those results yet. And not so long ago, here's another application. Not so long ago, I ran into this article here. Now that you know what to Google, you'll find it very easily, but it's a 2020 paper about discrete orthogonal polynomials as a tool for detection of small anomalies of time series, a case study of GPS final orbits. And these guys here go ahead and they claim they use order 300th polynomials, fits to their data, to extrapolate these small GPS satellites' error positions. So I'll just briefly here, I have one slide on this, but the idea was to show that these guys use 300th order polynomials. But it is a specialized technique. They do use hand polynomials, and I haven't looked into it or tried to duplicate it. I'll let that one of you guys here, you can go in and take a look at it. But what they say, there is a need to detect small discontinuities in orbits of GPS satellites published by the IGS, the International GNSS Service, as final GPS and GLONASS, satellite ephemerides, they call those positions that they have. And they say this is a typical graph of the coordinates of a GPS satellite. This is in kilometers over here, I believe. Vertical axis is in meters over here. And so they took this signal, or a signal similar to this, let's say, I don't know exactly, and they would get 384 points over 4 days. These little jump discontinuities here are at those day boundaries, and they did a 200th order polynomial fit to it, and so then you would subtract that fit as we did, with the clutter filtering, and what you're looking at here are the residuals. And what they claim here is that they can show residuals at these daily boundaries, and it turns out after collecting a day's worth of GPS data, they go ahead and they have to calibrate and unify all the data from all these GPS satellites to come up with a final positioning that people can go ahead and use to locate things. That's the gist of it anyway. And so the magnitude of these bumps are about 1 centimeter, or about 10 to the minus 9th of the GPS coordinates, and they claim that they can use this technique to detect these small discontinuities. I thought that was remarkable, and so there's another application here for these polynomial fits. So I think that's all I have. Conclusions quickly, I guess I have a minute. Try regression clutter filtering. You'll like it. Simulations show regression outperforms GMAP. There's a lot of simulations I didn't even show you. You can go into that paper that we have down at the bottom. There's all sorts of simulations in there, and we have more than that even laying around. Regression does not need a window function. That's the whole point, which reduces your independent sample. Regression has an adaptive bandwidth selection. That has been a barrier to using the regression filter, so we've solved that problem. Zero velocity interpolation is easy and straightforward, works very well. We have a lot of simulation showing that. Make sure you use discrete orthogonal polynomials. Go get that one from that guy's webpage. Download, it's either in C++ or it's in Fortran. Do not use local regression filters. You know, I told you about Torres and Zernick when they went ahead and they tried this technique back in 1999. If you go and you take a look at that paper, they talk about the theory for a global regression filter, but when they actually went to apply it, they used a local regression filter. Instead of filtering on the entire length, they used a 16-point series, and they marched that along with a little Savitsky-Golay type filter. And I was told by one of the authors when I was investigating that, I think you'll find that you won't get a very good clutter rejection. And the reason they weren't getting good clutter rejection is because they took the bait and went for that local regression clutter filtering rather than sticking to the global regression clutter filter. That's my opinion anyway, and what I think would happen. At least that's what they did in their papers. So with that, I'll stop and take any questions people may have.
Well, thank you, John. Thank you for sharing your research with all of us, and
Welcome.
Thank you for making applied math fun. It sounded fun. So we have people in the audience, and for those watching online, please ask your questions on the Slido window. Does anybody have any questions in the audience? So I have a question. So if you show that the simulations using regression outperform the GMAP, and you're the PI for the next RAD that's funded by the National Weather Service, is there any move by the National Weather Service?
Well, we're presenting that right now. We are trying to convince them of that. There's more to this whole story. We go ahead and we give presentations, what they call the Technical Advisory Committee, that kind of, not dictates, but suggests what things they want to go toward. And so it's pretty entrenched. GMAP has been around since, the 2000s, early 2000s. And all of their surrounding processing is, around that type of clutter filtering. They have another clutter filter, a little bit different from GMAP, that they're fond of because they developed it, right? We're all fond of the things that we develop. And so we continue to do investigations into that, and in fact, right now I have, in fact, I should go from here to my office and start looking at it. We have a bunch of NextRad data that we're applying this to, and there are some wrinkles in that data, and you can invite me back and I can talk about that and go into it. But it's the way that they do their processing, we have to take into account to it. They do things like super resolution data, and they use overlapping windows to do this super resolution data. So if you have 64 points, that's your 1 degree resolution volume, they like to chop that back down to 32 points. And this does give you increased resolution, which is important for detecting tornado genesis, for example. And so because of this super resolution thing, and then they also use SC phase coding on it, and I've talked about that, so we're on top of that too. And so all of these things combined together make it a little more difficult processing environment. So we're on it, and we hope that they will adopt it, but you don't know. There is politics in there also you're working against.
Because presumably, just seeing your results for like the S-Pol example, people will use some of that data and put them into their models and then use them for forecasting, for example. And so the more good data you can put into your models for parameterization, maybe you can close that gap on better forecasting techniques.
Bingo. Yes, that's what we hope.
Does anybody
Thanks
from
for the question.
Have any further questions? Bill?
So you showed how to use it for band stop filtering.
Yeah.
Did you say you can also use it for band pass filtering?
Well, yes, because remember when you apply a regression filter to your data, you have the mean trend, and that is an estimator of the low frequency content, and then you subtract that off, then you're left with the high frequency content. So you can either have a, you can either do one way or another. You can take a look at the high frequency components. To tell you the truth, we've just looked at the, the band stop capability where you want to get rid of clutter, but there's no reason why you can't use it as a band pass filter. I haven't done it though, and so in a lot of these things you want to do it first before you, tout it as a viable option.
Maybe there's a collaboration opportunity.
Yeah, let's collaborate, Bill.
Is any other questions? Hey, Andy. Oh, we've got a question. Very impressed with our audience.
The last time we chatted about this, my first impression was, or the first thought that came to my mind was that it's not time invariant. But one thing that had just occurred to me while I was watching this is that a window function is not time invariant either.
Mm-hmm.
So, and everyone uses window functions. So,
Yep.
so maybe time invariance is not the end-all be-all of what makes a good filter.
Yeah, that's a really interesting thing, and I keep thinking that somebody might have thought about these global regression filters and this whole issue about the time invariance and frequency responses. And I went over to the library and looked through all sorts of signal processing books. I got all sorts of signal processing books on my shelf. You don't see them talking about global regression filtering. Let's talk about regression, and then they go over and they do local regression filtering because they can get a convolution out of that guy, and they don't take a look at the globe. So I think there's a real large potential for somebody to really, dig into this and look into the theory and all that.
So it looks like we have a resident expert on regression and clutter filtering here at NCAR, certainly at EOL. Well, if we have no further questions, let's please thank our speaker, John Hubbert. Thank you.
Thank you.